So this video is to cover the questions that we had in class today that were really confusing. After looking at them for a while, most of them I understand, and some of them I'll understand later and I'll record those sections. But for now, we're just going to go through these. So, I'm just going to explain what's important about them and what is... Because I didn't... All of these are important to understand. I didn't get all of them wrong, but you might have gotten 1 and 2 wrong, and you got 4 and 5 right. So I'm just going to go over every single one. There are a few things I want to go over, though. And I will pull that up right now. Okay, and we're back. I have made a little acronym here. It is RAVE. It's some important things to follow when you do any kind of long-form math problem with a lot of words in it. I'm going to go through it when I go through the questions, just so I explain as I do things. So we're going to start on this question here. So this is a pretty short question, so we don't need to use RAVE here. The table describes rates of change of a function f for selected intervals of x. Okay. The function f is defined for x is greater than or equal to 0 and x is less than or equal to 4. On which of the following intervals is the graph of f concave down? So this is a very easy question, because as long as you pay attention to what what it's saying is increasing. So it's saying the rate of change. And as we remember from 1.1, concave down, which is what it's asking for, means that rate of change is decreasing. Does not matter what else is happening. Rate of change decreasing, that's concave down. There is no other option that says decreasing rate of change other than this interval right here. And that is the only one that makes it concave down, making it this interval that matches up, right? Very simple question. Now here, this might require a RAVE. So a toy car travels around a circular track as shown in the figure. As the toy car travels around the track, its distance from the wall could be modeled by a graph, where the y-axis represents the distance between the car and the wall, and the x-axis represents time. Which of the following graphs model this relationship as the car goes around the track 3 times without stopping? A lot of words here. So our first step is read and reread, because there's a lot of details in the actual problem question itself that are extremely important to the solution, because if you don't know what you're trying to answer, doesn't matter how many fancy formulas you know, you're going to get it wrong. Second thing to look at is your answer choices. So once you've read and reread this problem and you fully understand it, look at the answer choices. Now, immediately you can rule out some of these. For example, you can't have a negative distance away from a wall unless you want to drive through the wall, but you can't do that because you're on a circular track. So that immediately eliminates one of the options. And then once you see some options that could be right, like this one could be right, this one could be right, you start trying to think about how you can frame the equation to determine which one's correct. So, third step, visualize. This is one of the most important steps, because we are going to take the information that is just this huge block of words right here, and we're going to turn it into a picture, a pretty picture, because we love that. So, we're looking at a toy car traveling around a circular track. Okay, not as important, we have the visual for that already. As the toy car travels around the track, its distance from the wall is modeled by a graph where the y-axis represents the distance, okay, distance, and the x-axis represents time. Time. Got it? Which of the following graphs models this relationship as the car goes around the track 3 times without stopping? Okay, so we are looking for the distance from this car to the wall. right? So let's draw that out. So we have our wall, and we have our car. We have our circular track right here. Now, we are not looking at how far the car is along the track. We're not looking at how fast it's going. We are only, let's say it moves over here. The only distance we are looking at is this distance right here. Their distance, right? So let's just try to think to ourselves how that distance value changes as we go around the circle. So it starts off really small, right? Because we're right next to that wall. And then as we go out, since it's a circle, or really you can think of this as, here, let me get my marker here. You can think of this as two concave lines, right? Because the rate of change is decreasing, so it's concave down. So in a concave down line, you have a exponential increase. So the reason it's not something like this linear is because that linear, that would be if we're moving on a straight line, like this. Our distance goes straight up and straight down. But in this case, it's not so simple. This car here is still really close, getting a little farther, really far, and then it drops off at the end. They hit the brakes, and then pick up speed, and then they lose speed, right? So, and we need to remember that they're traveling at a constant speed over time, and the distance is the only thing that's changing in speed. So, if we know it can't be, you can't go through the wall. You can't go negative. That doesn't work, right? And if you know that you're not traveling in a straight line, so that doesn't work, and you're not continuing to travel away from the wall, then this is the only option. And it makes sense, because we're traveling away from we're starting slow, going fast, and then going slow again, and then coming back to the wall, and then going away from the wall, back to the wall, away from the wall, back to the wall. And then that is 3 repetitions, as it says right here. Goes around the track 3 times without stopping, so that's the correct answer. Next one we got here is graph the function f is given for x is greater than or equal to -3 and x is less than or equal to 6. Which of the following statements about the rate of change of f over the interval x is greater than 2 and x is less than 6 is true? A lot of words there, but what's interesting about this is half this graph we don't even care about, right? So half this graph we can just ignore. So let me just draw a red line right down the middle. I don't care. All this right here, not in our interval. Because remember, we have to be above 2 and below 6. So, and then we can cut it off right here as well. Right? So we don't care about anything else. This is all we want. So now that we've reread the question, we've visualized it. Now let's read the answer choices. So we're looking at rate of change here. Either rate of change is positive, rate of change is negative, rate of change is increasing or decreasing. Now let's take a look at this. Now it's really easy to say, oh, it's positive or oh, it's negative. But if you look at this midway through, it switches from going positive to going negative. So technically it's both. So you can't just say one or the other because in this interval it is both. So we can immediately eliminate these two choices. Now it's either increasing or it's decreasing. Now let's think about concavity. We are going up, but we're trying to decrease it as much as possible just to hit 0 and then come back down. That's concave down. Oops. So, and what is characterized by concave down is a decreasing rate of change. Oh, hey, look, rate of change is decreasing. Now this one I got wrong because I didn't follow the first step. So a ball is thrown through an open window to the ground below. the height of the ball in meters at a time t seconds after it's thrown can be modeled by the function h, given by h of t equals this thing. Which of the following describes the height of a ball above the ground? Alrighty, so immediately what we see is balls thrown through an open window to the ground below. We need to find the height after it's thrown. Sorry, I had a brain fart there. We need to find the height of the ball above the ground. Okay, so we just have to find the height of the ball around the ground. Cool. Now let's look at our answer choices. And we have to read them thoroughly, because it's really easy to get tripped up. After leaving the window, the height of the ball increases to its maximum height of whatever meters, and then the height of the ball decreases until it reaches the ground whatever seconds after reaching its maximum height. That is why I got this question wrong, because I didn't read that, I didn't see it, I assumed, which was wrong. So I'm going to pull up Desmos, and I'm going to throw the function in, because I don't have a graphing calculator, and I'm not about to buy one. So as you can see here, I've modeled our little graph here, and let's take a look again at, so we visualized it, so we know what it looks like. Let's take a look at our step 2. So we visualized it. Also, explain it to yourself. I forgot to cover that, but if you're not really sure on something, or even really most questions, you want to read your answer choice and explain it to yourself as if you're teaching yourself how to do it. Because teaching is the best way to learn something. But if it's only you, and you're doing a test, then just teach it to yourself, even though you know it. If you try to explain something to yourself, and then you realize, wait, how does this work? And then you have to really think about it, you could end up being wrong. Which is good because you caught it. But that kind of thing can help you double check your answers. I'm not going to cover it too much because I'm actively doing it this entire video by explaining it to you. So, after leaving the window, the height of the ball increases. Okay, so what we're looking for is the height of the ball above the ground at its peak. Maximum height, maximum height, maximum height. That's what we're looking for, maximum height. So, what is our maximum height here? Let's zoom in right here. Maximum height looks like around 16.22 something. And that immediately eliminates A and B because it's 16.228. That's the only thing it can be. Now, if we were to just look at the zeros of the graph, if we were to look at the zeros of the graph, we'd just say, oh, it's around 2.2. And here, yep, 2.269. Easy answer. But that's the amount of seconds after it's thrown, not after it reaches its maximum height. After it reaches its maximum height, we have to find that by getting this, which is 2.26 whatever, and then going all the way back up here and looking at this second value. So it's 0.44. So we'll take, let's see, 2.29 minus 0.4, that's around 1.8, right? And there it is. You don't have to be exact because it's multiple choice. And that's what you would choose because you read the question and the answer choices thoroughly. Okay, next one. The table gives characteristics of the rates of change of the function f on different intervals. Which of the following is true about f? Notice how it says f. It doesn't say which of the following is true about the rates of change. Which of the following is true about f, sorry. On the interval 3, 4. So really, we don't have to look at anything else but this interval right here. Now that we've read the question, we need to read the answer choices. F is increasing, concave down, increasing. So we're looking at either it's decreasing, increasing, concave up, or concave down. So let's visualize this. Positive and decreasing. If we are positive, that means we are going up. Some way, somehow, we are going up, right? But if we're decreasing, as we go up, we're going up a little less, right? So that's what our graph should look like. Now, this looks an awful lot like concave down, right? So it's increasing and it's concave down. I don't know what happened here, but it's increasing and concave down. Should have been an easy answer, but I probably just misread part of the question and then pressed something super fast because I wasn't following Rave right here. So this is the last one, and this one was kind of a head scratcher. So water is poured into an empty vase at a constant rate. A graph models the depth of the water in the vase over time. The graph can be described as follows. The graph is always increasing. The first portion of the graph is clearly concave up. The next portion of the graph has a fairly steady and steep increase. Which of the following vases is appropriate for the context described by the graph? Okay, and we look at our answer choices. Unintelligible. I don't know what to do with these, right? So what we're going to do is, first we're going to draw this graph. Because we've looked at the answer choices, looked at the problem, still stumped. We're going to visualize it. The graph is always increasing. The first portion of the graph is clearly concave up. So if our graph is concave up and it's always increasing, so it's concave up, and then it increases steadily at a fairly constant rate. That's what our thing's going to look like, right? Now what can we do with this? Why does this matter? Well, if we think about a bottle, or a container of any kind, the wider the base, the slower it takes to gain depth. Not volume. The amount of water we're pouring in is the same. Doesn't matter. Constant rate. However, we're looking for depth. So if it has more width, the same amount of water is going to cover less depth. So if we look at this bottom one, we are decreasing the rate at which we increase in depth because it's getting wider, right? The wider it gets, the slower it increases in depth. So this can't be it. This one right here can't be it. This one right here looks promising, right? Because, no, it doesn't actually, because it decreases in speed. It opens up, even though it does close up, it's decreasing in speed as it widens. If we look at this one's definitely more promising, because you have a concave up shape as it decreases in depth, it gets faster and faster, but we have the opposite out here as it widens. We need something that never widens, at least not too much, which lands us here. Perfect shape, we have the concave at the bottom, and then we have a fairly even, straight line. Perfect, right? And there is an AP video on this that is perfect. It like shows you, I believe it's in 1.1. If you want to see that, you should definitely check that out. It is very helpful. But that's all for Change in Tandem quiz. I'm going to be covering the rest on the channel, so check those out. But yeah, that'll be all for this video.